Because of its solid features, this would give us a much fuller image of the world to the extent that we may be concerned. Now, a great picture at any point seen was essentially taken by the James Webb Telescope. Go with us as we investigate the James Webb Telescope and how it could make everything unique. How everything began. How everything began after the telescope was first suggested in 1996. 3 gatherings of specialists and engineers from public and private sectors got together to really take a look at whether NASA could truly build the telescope. Each of the 3 gatherings showed up at a comparable goal. The telescope could be assembled. In 1997, NASA agreed to pay for extra assessments to chip away at the specialized and financial requirements. By 2002, the building of the telescope had chosen groups to build its most significant equipment and an advisory committee of analysts to help with the structure cycle. The telescope was previously named the James Webb Space Telescope that very year to honor the previous head of NASA, who made huge contributions to the development of the Apollo program. When engineers and researchers began assembling the Webb telescope in 2004, they expected to come up with new advances and procedures to meet the mission's serious science needs. Space voyagers could fix and further develop Hubble while working from Earth, yet Webb would have to take care of its responsibilities from excessively far away for Earth to assist. Notwithstanding these issues, the group wrapped up each of the 18 reflective pieces and put them through a rigorous series of tests to guarantee they fulfilled the rules. It was finally possible to picture the telescope going into space and doing its job. The James Webb Space Telescope was developed and worked from 2012 to 2013. Great bits of the telescope were being built in different places all over the planet. Building began on Webb's sunshield layers in 2013. These layers shield the telescope from excessive force and let it function splendidly in space. Throughout the following couple of years, Webb's special science instruments were put through extreme tests with high temperatures and shaking. All the while, the telescope's 18 separate mirrors were carefully set on its back plane. These parts were collected and tested at NASA Johnson Space Center in Houston, Texas. In 2017, the telescope and its equipment also went through one final round of environmental tests in a massive thermal vacuum chamber to ensure they would work properly when set into space. Webb was finally sent into space around Earth on December 25, 2021, at 7:20 a.m. Eastern Standard Time. So, how does the telescope really work? People often make space travel sound unnecessarily straightforward, so when you first learn about it, it could appear like simply another camera. That isn't the case. It's very surprising, which is the reason it took such a long time to get from concept to launch day. The James Webb Telescope is a powerful telescope made to see things in space that are too cool or weak for normal telescopes to see. These are things like stars, galaxies, and planets that are just beginning to form. The telescope is designed to identify infrared light, which is what these distant celestial bodies use to transmit most of their heat. This permits us to get more familiar with these things. Infrared light can't get past gas and dust, which makes it look cloudy to our eyes. Webb, on the other hand, can detect ultraviolet radiation as well as visible light and infrared radiation. This allows it to take pictures of things that are hidden by dust and gas, giving us a better view of events happening far away in the universe. It is also possible to concentrate on the properties of things on the planet, like their chemical composition and temperature, using infrared light. Infrared light is significant in many areas of physics and development. It can help us understand how stars, planets, and other astronomical objects are formed, as well as how they change over time. It can also be used to find signs of chemical contamination in our atmosphere. The telescope has a significant array of imaging and spectroscopy instruments, along with cutting-edge thermal control systems that allow it to work in harsh conditions like space. This is crucial because this camera is intended to go into space by itself. It must be built to handle anything out there with no support. After the telescope was sent into space and separated from its launch vehicle, it unfolded and began its long journey to its destination, going through a complex series of steps. There were a couple of critical stages in this cycle, such as crossing the moon and separating into various pieces. The telescope became one of the most useful resources of its kind when it was fully set up. Let's investigate the steps this essential telescope took to get into space. Before we talk about why it was so significant, the launch was the first thing that had to be done. The solar array was set up after the launch, and 2 extraordinary beds were deployed on the 3rd day of the journey while the shuttle was still inside the case. The significant sun shields for Webb were stored on these cases. These shields keep the telescope cool and allow it to work properly in space. The positioning of these shields was critical for ensuring that the camera could operate efficiently during its journey. On the 4th day, the tower that held the instrument package was moved to its final location and assembled. There were many complicated steps in this process. However, everything went smoothly due to how the telescope is assembled. The sun strain then raised the speed overlap, generating a force that keeps the telescope stable. Next was the arrangement of the sun shield layer cover, which revealed the tennis court-sized sun shields. After everything was set up, the sun shield and mid-perplex were sent. The 5 bits of the sun shield were then pulled apart. But this isn't the end. When the James Webb Telescope was placed into space, it had to go through several critical steps. The secondary mirror and a frame to keep the smaller mirror in place were set up on day 10. The primary mirror wings were then extended on day 13, which gave the telescope its final shape. After these means were finished, the telescope was prepared to start its job of noticing stars and planets far away. What is the genuine purpose? What's intriguing about the James Webb Telescope is that it wasn't simply made to do one thing. Many things are meant to be handled by it. We should dig into this further by going back into the past. Specialists like Daniel Einstein, a cosmologist at the Harvard-Smithsonian Center for Astrophysics, can utilize telescopes like the James Webb Space Telescope to go back in time and see galaxies when they were just starting to slowly form. Light travels so that a planet that is far away looks older than it really is. The telescope can look at the early history of galaxies to learn about how they formed and how they changed over time. By studying distant galaxies, specialists like Einstein can get a complete picture of how galaxies form and change over time. Webb is excellent for studying far-off galaxies since it can see infrared light. The universe is expanding, which stretches the light from these galaxies over time, transforming it from visible or ultraviolet to infrared. Webb is perfect at identifying infrared signals since it is large and cold, allowing it to see much farther into space than other telescopes. This enables it to observe galaxies as they evolve and take pictures of how they change over time. We can study how galaxies form and evolve thanks to Webb, helping us comprehend the universe better. Researchers can investigate how stars form. Stars are born from dense clouds of gas and dust called stellar nurseries. Since these clouds are so thick, visible light can't penetrate them, making it hard for scientists to study these areas using conventional optics. However, infrared light can penetrate the dusty clouds more effectively than visible light. This allows researchers to see into the core of these star-forming regions in ways that other instruments cannot. Because the Webb telescope can see infrared light, researchers will be able to study these areas in much greater detail than before. An infrared space expert at the University of Arizona named Maria is the principal investigator of one of Webb's cameras. She says this is because red light has a longer wavelength and can pass through the dust in our atmosphere better than blue light. Also, infrared light can penetrate dusty regions of space better than visible light. Because of this effect, the sun looks redder at night than during the day. Since Webb can see infrared light better, Hubble has only been able to focus on the surface development of stars. The broader scope of infrared bands on Webb will allow researchers to see deeper into the dust and study more about how stars are born and develop. Studying black holes is difficult since they can trap light, making them some of the most mysterious objects in the universe. However, we can see how black holes impact the stars and galaxies around them. Researchers have studied various aspects of black holes using telescopes like X-ray telescopes. For instance, they have analyzed how the extreme destruction of neighboring stars heats up and energizes the area around black holes. With the launch of NASA's Webb telescope, its infrared capabilities will allow researchers to learn more about black holes. They can study the cooler gases and stars that swirl around black holes, revealing more about these mysterious objects and the complex physics happening nearby. Scientists are still studying black holes even though they are not directly visible. They will continue to be a significant area of research in the future as well. Observing exoplanets can be challenging when you look at stars in dense, dusty regions of space. This is why we need telescopes like Webb. Optical telescopes like the Hubble Space Telescope can't overcome these obstacles. The cool thing about Webb is that it can capture the light emitted by the stars themselves, even through dust clouds. This means that researchers will be able to use the telescope to look at regions of space that are currently obscured. The James Webb Space Telescope can capture and analyze light from stars that are blocked by gas and dust. This will help scientists learn more about the stars and their properties. They will be able to explore the structure and composition of stars and understand how they are formed and how they change over time. Thanks to the new data, researchers will be able to observe stars in ways they haven't been able to before. Because of Webb's ability to capture infrared light, exoplanets, planets that orbit stars other than our own, can also be studied. This will help us determine whether life can exist elsewhere in the universe. Researchers struggle with finding exoplanets since they are small and emit very little light compared to the stars they orbit. They are often obscured by the glare of their host stars, making them hard to distinguish with ordinary telescopes. Scientists can use different techniques to find exoplanets and learn about their atmospheres, which are employed by the Webb telescope. By observing how a planet's light decreases when it passes in front of its host star, analysts can determine its size, mass, and temperature. Spectroscopy can be utilized to analyze what is present in the planet's atmosphere. We have already found many large exoplanets, but the telescope excels at finding smaller ones as well. Cosmologists will be able to study many planets, including those that are smaller and closer in size to Earth. With the James Webb Space Telescope, astronomers will be ready to study these smaller planets and their surroundings using the telescope's advanced instruments. This will provide a better understanding of whether these planets could support life. Studying exoplanet atmospheres is crucial. Seeing how light from a star goes through the atmosphere of an exoplanet is an important way to learn about it. When light passes through the atmosphere of an exoplanet, it leaves behind patterns that researchers can study to determine the chemical composition of the atmosphere. This is especially useful for identifying the presence of water, which is essential for life. Webb's high-sensitivity cameras will make it easier to recognize these patterns, allowing researchers to learn more about exoplanet atmospheres. They will be able to study the history and composition of exoplanet atmospheres thanks to the telescope. Webb can also observe how light changes when an exoplanet passes in front of its host star. This method can be utilized to determine the size of the planet and whether it has any moons or rings. All of this information will help researchers learn more about exoplanets and decide whether they have the right conditions for life. Scientists can study how planets form and evolve over time by figuring out how exoplanets work. Webb's observations of exoplanets can help us understand how our own solar system formed and how it functions. They can also shed light on how planetary systems structure and evolve over time. This will make it easier for researchers to study exoplanets and assist them in finding ones that could support life. Webb's cutting-edge technology will simplify the process of learning about smaller planets and their environments, which will help in finding planets that could potentially support life. These include near-infrared spectrometers used to measure the chemical composition of planets and mid-infrared cameras and spectrographs used to measure the thermal properties of planets. These instruments will allow researchers to learn more about the atmospheres and surfaces of exoplanets, which will aid in understanding their history and development. The James Webb Space Telescope, JWST, is a remarkable achievement in modern astrophysics, representing a leap forward in our ability to explore the cosmos. One of its key advantages is its ability to operate in the infrared spectrum, which is essential for observing celestial objects that are too cool or distant for optical telescopes like Hubble. This capability allows JWST to delve into the mysteries of the early universe, capturing light from galaxies formed shortly after the Big Bang. JWST is equipped with advanced technology that enhances its observational power. For example, its primary mirror spans 6.5 meters in diameter, significantly larger than Hubble's 2.4-meter mirror. This larger size allows JWST to collect more light, enabling it to detect fainter objects. Furthermore, the mirror is made up of 18 hexagonal segments, which can be adjusted precisely to focus light accurately. This innovative design ensures that JWST can produce high-resolution images of distant astronomical phenomena. Another groundbreaking aspect of JWST is its location. Positioned approximately 1.5 million kilometers from Earth at the second Lagrange point, L2, it enjoys a stable environment, free from the atmospheric distortions and light pollution that affect ground-based telescopes. This strategic positioning allows JWST to conduct long-duration observations, crucial for studying transient events like supernovae or the formation of stars. The telescope's scientific instruments are equally impressive. The near-infrared camera, NIRCam, and mid-infrared instrument, MIRI, allow it to explore the formation of stars and planetary systems in unprecedented detail. By observing the chemical composition and physical properties of exoplanets, scientists hope to find potential biosignatures, indicators of life, in their atmospheres. Moreover, JWST's ability to monitor the atmospheres of exoplanets during transits provides insights into their climates and weather patterns, potentially revealing conditions that could support life. The wealth of data generated by JWST will not only expand our understanding of the universe but also inspire future generations of astronomers and scientists, opening up new avenues for research and discovery. As we stand on the brink of this new era of exploration, the possibilities seem limitless.